All right, here is our video recap or kind of a rewatch of the notes that we've taken in Chapter 4. So we're going to skip a lot of the main stuff because we've written the notes fully out online for you that you can download. But let's go through the problems just one more time, maybe just to hear it back what we did. So we have four ways of solving. We'll see them as we go. The first way is what we would kind of call guessing and checking, or in other words, just verifying a point. And what we do here is we simply take the first equation, substitute the x value given in that solution up there, substitute the y value, and we ask ourselves, is that equal to 64? And I'll let you work that out, but 8 times 9 is 72. 72 minus 8 does end up being 64. And again, just verify that for yourself. Underneath, this one's a little easier to plug in. It's just 9 plus 8. Is that equal to 17? And that's true as well. And so the answer here is yes, it is a solution because it worked in both. Now, that's essentially the first thing we know about a system as a system's solution is that it has to work for both equations. But then we move to graphically solving, right? The first way is just kind of guessing and checking or verifying. The second way is graphing. And so what do we do with graphing? Well, let me zoom out a little bit to get both the equations in the graph here. We're just going to start graphing both lines and then consider both of them after. So my first line here is thankfully in slope-intercept form. It has a y-intercept at positive 4. And it has a slope of 5 over 1, which goes off the page, but I could also go down 5 and left 1. That still overall is a slope of positive 5. I could go down 5, left 1 another time, and I could draw that line. So there's my first line, but I'm not done because there's another line that has a y-intercept at negative 3. And it has a slope of negative 2 over 1. Right, we're just reading from that mx plus b form. And what we notice is both graphs share a point where they cross. It's this point right here. And that point exactly, the point negative 1, is the solution. That's all we care about. It's that single point where both graphs cross. And so now essentially what we can do is we can connect these two ideas and really say, what does it mean to be a solution to a system? Well, it's where two graphs will intersect, or it's any point that works in both equations. I guess I say or, but really I should be saying and, because you're saying the same statement. If it works in both equations, then it is a shared point on whatever graph those equations have. So the both are tied together. And so that's what we're doing in this whole section of 4.1. All right, well, let's look at just one more example here with solving by graphing. And the issue here is that y is not isolated. Now, thankfully, the equations look fairly similar. So I can mostly do the same steps every time. I'll subtract 3x. And I'll subtract 3x. Now your equations will always look similar, but we're also trying to show you one big idea in this example. So this is kind of a special case. We would then need to divide a negative 1, which would leave me with positive 3x minus 5, and which would leave me with positive 3x plus 1. And so this is now what we're graphing. I guess I'm putting a box around it, but in other words, this is our kind of like new start. So after all that work, I now have these two lines. Let me go ahead and graph these two lines. A slope of 3 and a y-intercept at negative 5. Well, let's get that y-intercept down. And then use the slope of up 3, right 1, up 3, right 1. And why not? We'll continue it because you just never know where it's going to go, or where the spot that you might want to see where they cross is at. All right, underneath we have a y-intercept at positive 1. And so again, notice every time we're restarting and always setting it at the origin and then moving forward. And if I still use my slope of 3 over 1, and that might be one little thing to notice there is, hey, that's the same slope I just used. Let me just make sure yeah, that looks right. All right, what we get is we get parallel lines, and so there's no solution to this. And y, well, remember what we just said above. A solution is going to be where the graphs intersect or where there's a value that works in both equations. And since these graphs will never intersect, that's what we'll say. We'll say parallel lines don't intersect. Then there can't be a solution here. All right, up next, let's review again the algebraic way of solving. So we've dealt with, hey, essentially guess and check, or just check this one point. Are you right or wrong? We've gone from graphing, okay, get things to slope-intercept form and graph them and see where they cross. And we now move into two algebraic ways of solving. We have substitution and elimination. Now, substitution, the first goal of substitution, again, you can kind of review the filled out notes for that section. But the first goal is to get one of your equations isolated. And I have that here in my first example on the bottom. So step one is like completed for you in a sense. Now step two says take that other equation, the one that isn't isolated, the one that doesn't have one single variable equals some stuff. So that'd be this top equation. This one doesn't just say one variable equals some stuff. It says 2x plus y equals 18. So we're going to rewrite that second equation with a big blank instead of the y, because y is my isolated variable in that isolated equation. So I'm going to take that isolated variable in the non-isolated equation and just draw a blank in the meantime. And now we're going to get really to the heart of what substitution is and the way we read equations. So again, this says 2x plus y is 18. Now the way we want to phrase this underneath is that this is saying y could also be written as, right, or y is for x. But it's nice to say it that way, as y could be written as. Because when you read 2x plus y equals 18, the problem is there's two unknowns. But we, underneath, were just told y could instead be written as something that has an x in it. And so what that allows me to do is it allows me to read this and say, well, 2x plus what y can be written as is equal to 18. Right? We're swapping out the left-hand side of this equation for the right-hand side of this equation from here to here is the only step we're making. But when we swap it out, that's what we call substitution. Well, this is some fairly simple algebra. The parentheses are redundant. It's just a big blank to show you there used to be a y here, and I'm about to fill it in with what this other equation says I'm allowed to. And I end up getting 6x equals 18, and I end up getting x equals 3. At that point in substitution, you take that one part of your answer, and we know it's a part of our answer because any of these systems have an xy point as an answer. So I've found the x coordinate, and now I need to find the y coordinate. Well, I can do that by just plugging this into any of my equations, and I'll plug it into the first. And sometimes we do label them like 1 and 2 with circles to say, here's the equation 1, here's equation 2. If I plug it into equation 1, that's going to be 2 times 3, because they told me x is 3, plus y equals 18. And if I work that out really quickly, that's 6. If I subtract that 6 to the other side, I'll get 12. But wait a minute. Maybe I'm thinking about another example. But I get 3, 12. And actually, yeah, that makes sense. Because if I plug that into both of them now, right? 3 times 2 is 6. 6 plus 12 is 18, yes. And then careful about the ordering here. Y, so 12, is that equal to 4 times 3? And the answer is yes. So I know I got the right answer because it worked in both of my equations. All right, let's still do substitution for number 5. The issue here is we don't have that first step already done for us. One of my equations doesn't have the variable isolated, but hopefully we can see that it wouldn't be too hard in the bottom equation to just subtract that 2y over. And if I do that, I've now gotten one of my variables isolated. So I'm good to go. So again, in that bottom equation, I just needed to subtract 2y, and then I got one of my variables isolated. And so now I'm good to use that substitution step that says, hey, you just found out that x could be written as negative 2y plus 10. So I'm going to take that other equation and say 5 times, not x, but 5 times negative 2y plus 10, because that's what it can be written instead as. All right, so 5 times all that new quantity plus 4y equals 32. As I work that out, I just have some distribution to do there. That's negative 10y. That's plus 50 plus 4y equals 32. Combining a few things here at the same time, the negative 10y and the positive 4 make negative 6y. Subtracting that 50 over makes negative 18. And I get y equals 3 again. Or I get, I guess, at least 3 as a part of my answer again. I put a box around it, but that's a little bit I did it there too, but we're not really done yet. There's only one answer. It's the whole xy pair. So I solved for y. Let me go back in and substitute it. Maybe I'll plug it into the bottom because it has less work to do. So x plus 2 times 3 is 10. Running out of space there. But if you look at that, that's 6, and if you subtract that over, you'll get 4. So careful when you write it down, it's 4, 3 because it's x, then y. And great, we just did substitution. So one thing to note is that, again, you might not always have an equation that is solved for a variable, but you can do that. Also notice it doesn't matter whether you isolate y and do substitution or isolate an x and do substitution. Now also it doesn't matter if it's the top or the bottom equation you isolate, it's just whichever one is easier. Alright. Underneath, let's go through elimination. Elimination, the idea is we're going to what we call scale these functions or these equations in ways that produce the same value but opposite sign in the equation 1 and equation 2, top or bottom equation. Let's see what we mean by that on this first one. We want to create the same value but opposite signs. And the thing about number 6 is, well, the 3's are already the same value. So I just need to change their sign. So maybe I'll just say, well, let's multiply a negative 1 to that first equation and see what we get. Well, that'd be negative 2x minus 3y equals negative 15. Underneath, I'd have 4x still plus 3y equals 21. Because all we're doing is, again, distributing that negative to the top equation, not the bottom. Now, because we now have the same value but opposite signs, we can go ahead and combine our two equations now. And this is kind of a funky step. It's kind of something you wouldn't think to do, that you can just push these two together in a sense, but you are allowed to. So negative 2 plus 4 is positive 2 with the variable x. Negative 3 plus 3 with a y is going to cancel out. That's why we call it elimination. And negative 15 and 21 will make positive 6. So we get 3 as a part of our solution. I won't put a box around it this time, though, because, well, it's not a final answer until I find the x and the y coordinate of that point where they cross. We'll plug this into maybe equation 1. And so that's going to be 2 times 3 plus 3 times y is 15. That's going to be, if I work that out, 3y equals 9, because I'll get 6 here and subtract it over. And so then finally I get y equals 3, and there was the 3, 3 I was thinking about above. And that's my answer for number 6. All right, so really, the algebra here shouldn't be too bad, but it's kind of the, I guess, what do I mean by that? Like, the actual algebra we have to deal with. We're just multiplying, combining some like terms, and moving stuff around. But the idea of how do I know what I'm multiplying? That's really what we're looking at in these next few examples, 7, 8, and 9, is how can you really determine what you need to multiply, and what's the strategy there? Okay, so for number 7, we have 4x and 5x. Now we could eliminate them by finding their least common multiple. We also have y and 2y. And the thing about having a single y, or a variable with a 1 out front, is it's really easy to simply just multiply 1 times anything you want and get that new result. So that's what we're going to do. We're going to multiply the first equation by negative 1, because that will create a negative 2y. And yes, the other stuff's going to change, don't miss that, but specifically That'll make a negative 2y, which will cancel with my positive 2y. All right? So when I do that, I'm going to get negative 8x. I'm going to get negative 2y equals negative 36. Underneath, I still have 5x. I still have 2y. And I have 24. I get to my combining step. That's going to be negative 3x. That's going to be negative 12. And I'll get x equals 4. I've got to plug that into one of my equations. Again, I know I'm going through that algebra fast, but that should be review from chapter 2 at that point, combining like terms. I know it looks a little bit different in the format, but we're not doing anything too intense there that we haven't studied prior. So again, that's why we're going through those faster. If you need more review, then make sure you go back to chapter 2, which is still on the exam that this is in as well. So reviewing that still benefits you here. Anywho, we need to plug this 4 in. And if I plug that into the first equation, and to save some space, 4 times 4 is 16. So we'll say into equation 1. We now have 16 plus y equals 18. And so that'll give me y equals 2. And so I now get 4, 2 as my answer. Again, we should plug it into the other one just to be sure. So 4 times 5 is 20. 2 times 2 is 4. And guess what? 20 plus 4 is 24. So I'm pretty convinced I got the right answer since I found my other part by plugging into 1. And I verified my result by plugging it all back into 2. All right. Let's move on and show you that sometimes you don't have an easy way out in elimination. So, in the first example, the 3's were, I guess we would say maybe like very compatible, right? We just need to change one of their signs and we're good to go. Underneath, 1 and 2 are super compatible because you just need to multiply 1 to whatever you want. But next, 2 and negative 3 aren't compatible easily by just changing one thing. And 3 and 7 also aren't easily compatible by just multiplying one thing. So the issue here, the idea here is that you might have to multiply equation 1 by something and equation 2 by something else, and you're totally allowed to do that in order to create the same value but opposite sign. Now from there, what should we do? Well, for our x's, their least common multiple would be 6. So we'd actually just multiply 3 and multiply 2 here. Now that is maybe something you could do is you can just lazily, so to speak, notice that you can just multiply the other number to the other number and you're good to go. Similarly, in this case, 3 and 7 don't share anything in common. So really, you do have to multiply this by 7 and this by a 3 and make one of them negative if you wanted to eliminate your y's. But there are times where you can find like a better choice than just multiplying the entire other thing. But really, in this one, we can't because 2 and 3 don't have any common factors. 3 and 7 don't have any common factors. They're going to need each other multiplied to themselves in order to do elimination properly. Okay, so that is what we're going to do. We're going to multiply 3 to equation 1. We're going to multiply 2 to equation 2. We'll put a multiplication dot just to make that clear. And let's see what happens when we do that. Carefully, 3 to the entire top equation will be 6x. It'll be 9y. And it will be 96. On the bottom, 2 to negative 3 will be negative 6. And now we know the elimination will be good. We have to keep multiplying that 2 everywhere. That'll be 14y. And that'll be 88. All right, we get to our combination step. The 6's cancel. 9 and 14 make 23y. And 96 and 88 make 184. All we have to do there is divide the 23, and we get y equals 8. And I guess let's still just plug that into 1. So when we do that, what we're going to get is 2 times x. If I work a little ahead, that's going to be 24 equals 32. I can then go ahead and subtract the 24, and I'll get 8. I can then go ahead and divide the 2 and get 4. And so now, careful, it's 4, 8. And let's again plug that in and verify. So let's see here. We can use a calculator to do that just a little bit more quickly. Negative 3 times 4 plus 7 times 8. That is indeed 44. And 2 times 4 plus 3 times 8 Yep, is indeed 32, so we are good to go there. All right. Up next, this one is going to be the trickiest one of the bunch because it's got all these fractions. And so the key here is that maybe before you do eliminations, we just get rid of fractions entirely. So that's going to be my first step. And to do that, we're going to have to remember that we can multiply by the LCD, the least common denominator. Or in other words, the least common multiple of your denominators to get rid of your fractions. So let's do that. If we multiply the first equation by 4, all of those denominators can divide cleanly into. So that'll work. And hear me out when we distribute this 4 through. 4 divided by the 2 in the bottom is 2. That result times the 3 left over is 6. 4 divided by 4 is 1. 1 times the negative 3 is still negative 3. And 4 divided by 2 is 2. And 2 times the remaining 9 is 18. So we're good there. Underneath, the bummer is that 5, 4, and 10, their LCD is actually 20. All right, so we're going to get maybe some larger numbers here. 20 divided by 5 is 4. 4 times the remaining 1 is still 4. 20 divided by 4 is 5. And 5 times the remaining negative 5 is negative 25. And 20 divided by 10 is 2. And 2 times the remaining negative 17 is negative 34. At this point, it's tempting to, draw the line underneath and combine. I almost just did, but wait a minute. I still haven't actually done elimination. I've just gotten rid of fractions. Now, that's still a necessary first step, but don't forget that now we actually have to go through the elimination process and say, okay, what would be the easiest thing to get common denominators with? And again, thinking most efficiently as a mathematician, that choice would be making 12 out of 6 and 4. Because 6 and 4 share some things in common. They already share a divisibility by 2. So you don't need to multiply, 4 entirely here and 6 entirely here and make 24. Could you? Yes. But can you do a little better and have some smaller numbers through your multiplying? Yes, by again taking equation 1, this new equation 1, and multiplying it by, negative 2, because we have to make one of them negative, and multiplying this bottom equation by positive 3. If I do that, well, negative 2 times 6 is negative 12. Negative 2 times negative 3 is positive 6. And negative 2 times 18 is negative 36. On the bottom, 3 times 4 is positive 12. That will be my elimination. 3 times negative 25 is, negative 75. Negative 75. Y. Goodness. And 20 times negative 34, is negative 680. All right, we get to our combining step. The 12s cancel. Positive 6 and negative 75 make negative 69. Y. And let's see here, negative 36 minus 680, and a negative 680 make negative 716. Thankfully, though, when we divide negative 716 by negative 69, I made a mistake somewhere. I was going to say it cancels out nicely, but I've made a mistake. Where did I make the mistake? Give me a second. Goodness, I saw my mistake. For some reason, in my mind, I looked up ahead and saw the 20 up here and decided to multiply 20 again to the negative 34. But careful, I'm right here. I'm multiplying 3 to the negative 34, and that's going to be negative, let's see here. 3 times negative 34 is negative 102. Okay, there we go. Now, negative 102 minus 36 is, negative 102 minus 36 is negative 138. And thankfully, negative 138 divided by negative 69, there we go, is positive 2. All right. So, again, check yourself for mistakes afterwards. we would have figured this out eventually when we tried to plug stuff back in and got some really ugly answers. But again, check your work, follow the steps carefully. Let's continue. So from there, we have y equals 2 by itself. Now the thing is, we need to plug this y equals 2 into something to figure out what x is. And I'm just going to tell you, it would be awful to plug 2 into either of these because we'd be back with dealing with all these fractions. But you could plug this y equals 2 into any of these two equations because they're still equivalent. All we've done is what we would call scale these fraction, initial equations. But as long as you're scaling correctly and doing correctly to the left what you do to the right, same number every time. That was my issue here, right? I mixed up not doing the same number, the 3, to all the parts at the same time. But as long as you do multiply the same number to both sides every time, then you're good to go. So I'm going to plug this y equals 2 back up into this new top equation here before we got to our combining step. And so plugging y equals 2 into that would be 6x minus 6, because I'm plugging 2 with a negative 3, equals 18. That's going to be 6x equals 24. And so that would be x equals 4. So I get 4, 2 as my final answer there. All right. Now we should plug that into this one just to verify that. 4 times 4 is 16. 16 minus 50. 16 minus 50. Yep, is indeed negative 34. And if you really want, take that 4 and 2 and plug it into maybe one of those, and the fractions will be ugly along the way, but at the point that you're just plugging 4 in and 2 in and evaluating to make sure it makes 9/2 or 4.5, that's not too hard of a check to verify. And in fact, just to show you what that would look like, for the sake of practice, if you took, your 3 over 2 and then multiplied 4, and then you subtracted 3 over 4 times 2, you can see I get 4.5, and then you can just even say, well, is 9 over 2, is that same decimal? Yes, it is. Well, then great, I know I did it right. All right? Sorry for a few of the little mistakes there with the algebra, but hey, stuff happens. We're probably not going to get 100% of everything right every time we sit down to do the math, but that's why we try to do as much as we can in the homework so that it's comfortable and we have time to sit back and check our work. Because at the point that I got whatever I got here, number one, it was a really ugly decimal. Now you might get some fractions as your answers, like 3/2 or, 2/3, some recognizable fractions. But if you get something that looked really nasty, then that's kind of your cue that, let me go back and check what I did and make sure that I haven't missed anything earlier. So just a note on that. Okay, now here's what we're going to do for sake of time and the sake that the notes have already been filled out. We already have now 6 examples of doing elimination. And we've even covered within elimination kind of the 4 different scenarios of really easy, just negate something. Maybe multiply just one thing because you conveniently had a 1. Maybe you've got to scale both. And maybe you've really got to say, I need to do some fraction cleanup and then worry about my elimination. And in this case, it still had 2 things needed to be switched in order to get that elimination in that elimination step. So we've really seen it all. And so what we're going to do now in 4.3 is we're going to not actually solve the system, because you can read that in the notes. We're going to spend all our time here just acknowledging how to set up these questions. Now, again, in the notes, we say there are 3 setups. We call them, or I call them, the counts and weights. Now, weight is kind of an interesting word. You could call it weight, worth, or scale, something like that. And we've talked about scaling. Scaling means multiplying through. There's a second one, and this one is not nice, but it's the substitution or forced approach. And we'll talk about what that means as it shows up in the examples. And step 3, or version 3, is what I would call similar description. Now, these are just kind of things to notice, and you'll hopefully by the end of these 5 examples see, okay, I can kind of identify where some of these things come into play. And this isn't a catch-all for every word problem that you'll ever see in all your math classes, but just kind of while we're here in this section, these are the three that you kind of want to just have mentally going for you as you go through the homeworks and the quizzes and exams, to be looking out for, okay, is it this scenario, or this scenario? Now, honestly, if you do your homework enough, the same question about the dollar bills is going to be the same setup, right? So you can either learn the three general setups, or you can learn that when they ask blah question about blah items, I know which scenario I'm in as well. Just throwing that out there. Okay, now let's go through the first one. And again, we're just worried about the two equation setup. We're not worried about solving because you will mostly use elimination for all these, or maybe substitution because it's forced. But we can practice that later, or I guess we already have practiced that earlier, and you can review that later if you have to get the answers to these questions. So again, let's work on the setups. Now the idea is we have a total of 56 bills, $1 and $10 bills, and they combined have a value of 191. Now this would be what I would call the counts in weight, or counts in worth, or count in scale type of setup, because you have the count of bills and you have their weight in bills, or in other words, their worth in bills, or the, that kind of mental idea. And so the idea is we can form these two equations like so. We can form a counts equation, which is just however many ones plus however many tens must equal 56 bills, right? I'm just worried about the count of the bills. And now I form a second equation, and I say, okay, now I'm going to take the X bills and multiply them by their worth, the $1 bills, and multiply them by their worth or their weight. I'm going to take my Y bills and I'm going to multiply them by their worth or weight. And then I'm going to have my monetary value, which is 191 at the end here. Now this is your weight or worth equation, because now you have the worth equals the worth at the end there, right? You have your counts equation, you have your weight or worth equation, and that's your setup. And you can see that this is actually a prime time to use elimination and just multiply a -1 to get rid of your x's, and so on and so forth. But there's the setup to that one. All right, there's again a total count, there's a total worth, so you create a count equation and a worth equation that, notice, gets scaled. All right. Up next, it says, in a certain year, a movie and its sequel grossed a combined total of that many millions. And then it says, if the sequel grossed 117 more than the movie, then how much did each gross? So maybe we could say movie and sequel, right? You can choose your own variables. You don't always have to use X and Y. But the movie plus the sequel from that first statement, we know made a combined worth, addition worth, of that much. That's your first equation. Now the question is, what's your second equation? And the idea is this is where we're in scenario 2, where you kind of have the second equation forced on you because they literally write out in words an equation to use. So it says the sequel grossed, or was, or earned, like it is, 117 more than. Remember, even though more than and addition doesn't matter, you should switch the order whenever you read blank then in your word problem setups. And that's it. That's all that this setup takes, is noticing that the first sentence is telling you that, hey, those two movies added together made that many millions. And then noticing the second equation is told to you directly in mathematics speak, the sequel is 117 more than the movie. So S is M plus 117. Again, the order should flip when you say blank then in your translating words to math equations. All right, so again, a pretty easy setup. Now this one also, just notice, is a substitution setup because this second equation says S can instead be written as M plus 117. And again, look at the field notes to see what we did with that. Now number 3, I'm not going to lie, is a tricky one because of all the numbers in the word problem and realizing that some of them are descriptive and some we actually need to use. So what I'm going to do is I'm going to say that, hey, the 18 and 22 inch wreaths, let's just call those small and large so that we can just read this easier. All right. 22 is again large, and this is small. I think that just makes our life a little bit easier, and we'll use L and S, large and small, as we go through the problem. Now that we've rewritten that, let's actually read it. A store sells 2 sizes of wreaths. The small wreath costs 25, and the large wreath costs 30. In one day, the number of large wreaths sold was 6 more than twice the number of small wreaths, for a total of 775. How many of each were sold? Now this time, you don't just have like a counts equation. You don't just have the regular just addition of the two, because notice you have the wreaths, their monetary amounts, and then the total amount that you got. So your first equation is going to look like this. Again, small is 25, so for the small wreaths, I get $25 per wreath, so 25S, plus 30L, so 30 per large wreath, should give me the 775. And that right there should be reminiscent of what we did on the first example. It was just the second equation that we had. Right? So however many small wreaths I sold, I got $25 for them. However many large wreaths I sold, I got $30 per each of them. And at the end of the day, I had $775, right? Hopefully reading that afterwards makes sense as an equation and why we should be using it in this one. Now, the second equation we have, again, if you read that second sentence, there's a lot of funky wording there. And that funky wording is once again forcing your hand. This is another one of those substitution where we need to use that equation they told me about. So it says, in one day, the number of large wreaths was, or is, 6 more than, so plus 6 at the end, we switch the order, twice the number of small wreaths. So that's your second equation. It's again forced by the wording of the question to say, you have to use this kind of translate sentence to math statement. All right? And again, you would use substitution. We can see that in the notes online of what the answers ended up being. Up next for number 4, this one is a little bit different. It's still in its essence a counts and weight equation, but the issue is we've got these mixtures and there's going to be one additional thing to watch out for. Now my first setup here, again, let's read it. There's one that has 25% concentration, another has 5% concentration, and how many liters of each should be mixed to get 20 liters that have a 19% concentration. Now this one is a little bit tricky. Again, we'll let X be the 25% juice. We'll let Y be the 5% juice. And my first equation here feels familiar, or is fairly easy. Usually the first equation is. It's just however many liters I used from the first and however many liters I used from the second, I know needs to make 20 liters. Now, this is where it's a little different because we're talking percentages and not like dollars or some other kind of summed amount. Percentages just behave kind of differently, and our second equation will look fairly similar, but it will be a little bit different at the end. Let's see what I mean by that. Well, I'm going to take my X, which is my 25% concentration, and I'm going to actually write 0.25X, or in other words, multiply it and kind of make that worth style equation, or weight style equation. And then up next, I've got 5% concentration. Careful, that's 0.5Y. And then what do I set it equal to? Now what's tempting is to set it equal to just the 0.19. But because of the way percentages work, we actually need to multiply the 0.19 by the total amount of liters used in the end to get your valid concentration. That's the big key right there, is that step. Noticing that when you're dealing with combining mixtures, again, it's just a little bit different, or when you're dealing with percentages as your weights, you're going to actually take that final percentage and multiply it by the total amount at the end in order to correctly solve it. All right? Up next, we have This year, senior class high school A and senior class high school B both planned trips to the park. At high school A, they rented and billed 16 vans, 8 buses with 752 students. B rented 5 vans, 5 buses with 380 students. And then they essentially want to know how many students can a van carry, how many students can a bus carry. And so really that's the question is B and V are unknowns. The amount, sorry, I think I read that whole thing without it maybe being visible. But B and V are the unknowns that we're looking for. And this is finally a matter of a similar description question because they said essentially the same thing twice. Blah vans, blah buses, blah students. And then blah vans, blah buses, blah students. When you say the same thing twice, that's telling you you're almost going to write the same equation twice. 16 vans plus 8 buses should give you 752 students. And underneath, 5 vans, 5 buses should give you 380 students. And this would be another question that is probably most suited for elimination, but it still would take some work to get to the final answer. All right, but those are your different scenario setups. Again, each one has their own little different flavor. Just be careful as you go through and take your time. All right. Finally, we get to 4.5, and this one shouldn't be too bad if we took to heart our graphing from Chapter 3. We really just have a few more lines to graph and things to review. The thing we need to be careful of is that we isolate y correctly. So when we isolate y, and again, for sake of time, I'm just going to show you what the final thing is once you isolated it. We'll have negative x plus 3 because I just need to subtract x over. The other one's a little bit trickier and I got to really be careful. And we need to subtract x, then divide a negative 1. Now be careful because when you divide a negative 1, you flip the direction of the inequality. And now I got to really be careful mentally. I would have subtracted an x over and it would have been negative x. And then I would divide a negative, which would make it positive x. But then there was that positive 5 over there and the negative would eventually divide it. Again, we can see that in the notes when we write it out, but there are 2 steps there on the bottom. The first step is just subtract the x, rewrite it, then divide your negative 1 in front of the y, and you'll see what we got there just in one step. All right, well, let's graph this and see what it means to be a solution to a system of inequalities. Now, what I'm going to do is I'm just going to graph each one as I go, and not graph both and then worry about the shading. So let's see what I mean by that. For the first one, I've got a y-intercept of 3 and a perfect slope of negative 1. Just looks something like that. Close enough to it. And then for my second equation, I have a y-intercept at negative 5 and a perfect slope of positive 1. Now what's interesting is I do see where both of these graphs cross exactly, but we're actually less concerned with the exact spot they crossed, and whoops, I forgot to do each graph one at a time. I'll do that next time, but after I've graphed both of these, be careful. This is why you usually might want to do your shading one at a time before you graph the next one, is you then need to go back in this case, first and ask, should this be a solid line or a dashed line? And so, whoops, out of force of habit, or maybe I did that on purpose just to remind you that it probably happens to you, I need to make this a dashed line. And so for sake of time, this is the easiest way to do that. Great, now it's dashed. But your online tool will be what you use on your exam, so don't worry about, erasing that carefully because you can just digitally change that you want it to be dashed instead. Anywho, now let's look at this. It says y values greater than this line. Now this line, again, is the one, this first one is the one that has the y-intercept at positive 3. There's a y-intercept at positive 3, so we're talking about this line. And we want to shade the y values greater than this line. And so let's do that. And greater means up, so notice I'm literally just shading up. Now up next, this other one says shade the y values greater than the line that intersected at negative 5. So here's that line, and if I start shading here, but maybe I'll just shade in a different direction, but I am still really going up. Notice that right here, in that section, that's where I get, I guess, kind of, a crossing pattern because of the way I decided to shade those just for a different visual since I just have a pencil here. But your paint bucket, so to speak, if you remember doing your homework, goes right here because it's now where do both of those shaded regions start to overlap with one another. And that's right here in this case, the top section. All right, let's keep on moving. Again, be careful when you isolate y for both of your equations. For this top one, I'll need to subtract 3x, and then I'm done. So that's going to be a negative 3x and a minus 5. On the bottom, I've got kind of that two-step thing again, where first I would subtract the x and make it negative, but then I would divide that negative and again flip the inequality, making the x positive and the 2 negative. All right, again, this bottom one is 2 steps. First, subtract the x and just see what you get. Then divide the negative in front, and remember when you divide a negative, it flips. And make sure that negative goes to all parts, and you'll see how we end up here. All right, let's graph these two real quick. We've got a y-intercept at -5, and this time I'm going to use my line or intercept and slope and graph, and then shade right away so that I don't miss that. So I need a slope of 3, 3, 3. Also, carefully, before I draw a line through it, I'm going to ask, should it be dashed or solid? In this case, it should be solid. Oops, there we go. And I'm going to go ahead and take care of my shading now. It says I want the y values greater than this line, so that would be all of this. This is where the y values are greater. All right. Up next, let's do the other line. We got a y-intercept at -2, so there's -2. And we have a slope of perfectly positive 1. And it should be solid as well. So there we go. And again, now that I just graphed that line, I want the y values above that shaded region I have, which would be here, but I can already notice there's nothing there, so don't fill it in, or here. So actually for the second time, and maybe it's not too surprising that since both of these said shade up and both of these said shade up, we ended up shading the literal top region of both. There is some, again, not coincidence to that, or there's a reason why that's happening, but don't let that concern you too much. This time, again, just say, oh, well, I started, again, if I did shade this second one truly correct, if I was shading above, I should say, well, wait a minute, there's nothing here anyways, but there is definitely stuff over here. All right, and there's nothing on the bottom, right, because we didn't shade the bottoms twice. Definitely not. Anywho, let's look at the next one. The next one is a little bit tricky to move things over, so I might actually do this in a few steps this time. My first step on this first equation is actually going to be to just rotate the whole thing around. Now watch when I do that. If I swap the order here, notice how I ended up switching the inequality as well, because, right, when we talk about inequalities, we usually say the silly phrase like the alligator's mouth open towards the bigger thing. Well, since it was opening towards 4x, if I want to rotate the whole thing, it better still be opening to 4x. For the other one, I'm just trying to get y by itself, so what I would do is I would subtract that 4x, and I'd still have -5. Moving on then, now to get y by itself, I would divide -3 on that first one, which would flip the inequality, careful. I would get -4/3 x, and I'm done. Underneath that, if I divide 3, I would have y is less than or equal to, and then, careful, -4/3x, and then also it divides everything, so -5/3 as well. Now this is definitely a funkier one for two reasons. Number one, this one doesn't have a y-intercept, and number two, well, it does, but we just don't see it. And number two, this one's y-intercept is a fraction, and that's not fun to deal with. But also, here's one idea. We have parallel lines again. Interesting. So let's see what happens here. When I graph both of these, I have a y-intercept at 0 for that first equation. That's the trick there. And then from there, I need to move down 4, right 3. I could also move up 4, left 3. And this needs to be a dashed line. And they want me to shade above. All right, let's graph the second one. The second one's y-intercept is at negative 5/3, so I go down 1 and down essentially 0.67 repeating, so I should be closer to 2 than I am to 1, and I'm somewhere in between. But the key here is, even though this is a really ugly y-intercept because it's a fraction, I can still actually move down 4 and right 3 and use that slope. So down 1, notice I'm still in between, 2, 3, 4, again I'm still in between, right 3. And these are really close together. If I go, whoops, did I go down 4? 1, 2, 3, 4, right 3. Oh, I went down 5 for this one. I thought something looked odd when I drew it out. There we go. It's late. All right, up next, if I go up 1, notice it's still between 2, 3, 4, still between, and go left 1, 2, 3. I'm still between here. And this one would be a solid line. And this one wants the y values less than that line I graphed, which would be down here. And so the issue is, since no region overlaps, there's no solution to the entire problem. Interesting. So it is possible to get no solution. It's possible that no shaded regions overlap, and that's probably only possible. I'm going to say it is pretty much only possible in these parallel line equations, because that's where you have the potential to have lines that will never cross. So there's, again, in this specific scenario, when the one above goes up and the one below goes below, there's no chance for any interaction because they're never going to cross, and so those shaded regions will never start to overlap. All right, one more real quick. We've got a special line here up first, and we've got one little, again, move some stuff around before you get started. All right, if I subtract the 5x and divide the negative 4, again, I divided a negative at some points, the inequality will flip. I would have subtracted 5 and then divided negative, so that would have double negated. And then that plus 20, if I divide a negative 4, would end up being minus 5. All right, and let me just, you know what? Again, because it's getting late, I don't trust myself, so I actually am just going to do this in pieces. I subtract the 5x, I still have the 20, and then now it's just easier to see. Don't try to do too much in your head if you can't. Divide the negative 4, done. Inequality flipped, great. And then from there, negative 5, negative 4, positive 5 over 4, and then 20 divided by negative 4 is negative 5. Great. Let's graph that second one first, because it's most like what we've just been doing. There's a y-intercept at negative 5, and then I've got a slope of up 5, right 4. And I could go up 5, right 4 again, which would take me just a little off the page. And careful, this is a dashed line, because it didn't have the or equal to. And now that this is isolated, I want the y values below, which would be somewhere over here. Great. The last line there is a special line, and it only has one variable. That's what makes it special. And remember, when you see one variable, the little phrase you say to yourself is the variable you see is the axis you will cross. So I will cross through the x-axis at 3, and that will be a dashed line. All right, now from there, this is the one time where we don't say shade above or below, because this is an x value. X values go left and right. So if I want x values that are greater, I'm going to the right, and so that's the shaded region where they overlap. And believe it or not, that's all of Chapter 4, so happy studying, and as always, if you have questions, send an email over or meet me in the office hours, and we'll do our best there, but hopefully this and the notes are all you need to get through Chapter 4. Best of luck.